All right, here we are again, 4.1. This is 4.1 part 2. We're solving systems of linear equations in two variables. At the end of 4.1 part 1, I said, oh, now we're going to talk about the other two types of equations. I didn't mean two types of equations, I meant the two other methods. So 4.1 part 1 was all about graphing, and we could visually see, and we did examples of each of these intersecting parallel and coincidental lines. But these next two methods, substitution and elimination, are purely algebraic. That means that we will not graph these. We won't look at these on a XY coordinate system. We will only use algebra to figure out the solution here. So we're going to manipulate these equations using algebra. But again, you'll never see them on a XY coordinate system. So we're not visually going to see these. All right, so when we substitute, what we're going to do is we're going to solve one equation for one variable. Well, the equation that I'm going to choose is equation 2, this line 2 right here, and I'm going to solve it for y. I'm going to solve it for y because it only takes one step to get to y. So I've chosen my one equation, I chose line 2, and I'm solving it for y. So I chose that variable. So what this says is that y is 3x plus 3. Well, if y is this, again, this is a statement. It's saying these are the same thing. This is this, this is this. So if y is 3x plus 3, then I can take that value and I can substitute it back in here. The reason why we're going to do this is because this will make it so that I only have one variable to deal with. So it'll say 6x minus 4, but y is this. So I'm going to instead say, no, y is 3x plus 3. It's not y anymore because I can substitute it because they're the same thing. So I can switch them out for each other. Okay, now notice here, important thing, that I chose line 2 to solve for y. I cannot plug this 3x plus 3 back in for this y. That would be bad. Okay, so I have to substitute it into the other equation. So it has to go into the opposite equation, the one that I didn't solve for. Okay, now that I've done this, I'm going to go through my regular steps and say, oh, okay, well, to get to x, I want to distribute here. I'm going to get 6x minus 12x minus 12 is equal to 10. I'm going to add the 12 to both sides and combine my like terms here. So we have that negative 6x is equal to 22. When I divide by negative 6, we get that x is negative 11 thirds when we simplify. Now a lot of people are like, booyah, bam, I'm done here. But remember that there's no point on the XY coordinate system that doesn't have an x and a y. It has to have an ordered pair. So I know what x is, but I don't know what y is. Well, now that I know what x is, I can take now, I've solved for the value for this variable. Okay, now I'm going to take this value and substitute this value into an original equation. So I'm going to take it and sub it back into line 2. So if x is this value here, then in line 2, I'm going to substitute this value for this x. This is like Houdini magic. Kind of running out of space here. Okay, well, these 3's will cancel. Negative times a negative is a positive, so I get 11 plus y is equal to 3. When I subtract the 11, then I get that y is equal to negative 8. All right, so yes, I now have my x coordinate and my y coordinate. X is negative 11 thirds. When x is negative 11 thirds, y is negative 8. This is my ordered pair solution, which it has to be written as an ordered pair. Okay, so this is the solution, not this and not this. I have to have it written as an ordered pair. Okay, so let's go through these steps again real quick. I chose equation 1. I solved one equation for one variable. I chose I can choose these. I can choose which equation and I can choose which variable. I chose this one because it was really simple to solve for y. I substituted the value that I got into the other equation. I solved this equation then for x. I got the value for x and substituted that value back into an original equation, back into this one right here, and solved for the other value. It spits out the other variable. Whether if you solve for y, it'll spit out x. If you solve for x, it will spit out y. Okay, and then I made sure to write my answer as an ordered pair. Now I'm going to go through this last part right here, which is to check. Remember, we're going to check by saying, are they both true statements? All right, so my ordered pair that I got then for the solution is -11/3 and -8. Well, let's plug them back in and see if these statements are true. This is how you check. Okay, so if I plug 11/3, -11/3 into the first equation and -8 in for y into the first equation, this 3 goes into this 6 twice, so 2 times -11 is -22. -4 times -8 is a +32. So 10 does indeed equal 10. This is true. So we know for a fact that this point lies on this first line. What about my second line? If I substitute -11/3 for x in my second line, and I substitute -8 for y in my second line, then these 3's cancel. A negative times a negative is a +11. -8 is equal to 3. Well, 3 does equal 3. This is a true statement as well. So I can verify then that this ordered pair is the solution to this equation. And again, we can do all of this without having to graph. So this is the process for substitution. I'm going to give 3 more examples of substitution. And hopefully this will be helpful. It's important to notice that this solution here algebraically says, oh my gosh, these lines cross because we got an x and a y value. So a couple things I want to point out about algebra. You can get a value of x can be 0. So x or y can be 0. Okay, x or y can be 0, but you'll get a value. If x equals 0, then x equals 0. If y equals 0, then y equals 0. Or if they both equal 0, all that would mean is that my lines, whatever they are, say that like they were this and this, they cross at this origin here. So that would be the point 0, 0. So x or y or both can be 0. Okay, algebraically. But I will get an actual value for x or y. That's really important to note. So if I get a value for x or y, I know instantly that these intersect. Okay, well, let's do another system here. And again, I'm going to give 3 more examples on this one. So this is all substitution. Okay, so the easiest equation I think probably to solve for here would be to solve the first equation here for x. So I'm going to take this line 1, okay, and I'm going to solve it for x by adding x. So I've got a -x plus a 3y is equal to 6. Sorry, I'm not going to add x. I am going to subtract 3y. Because I'm isolating x. I'm not putting this in slope-intercept form. I'm just choosing a variable, and the easiest variable of this is going to be x. So I'm going to get a -3y plus 6. Then I'm going to divide all these by a -1. And I get that x then is equal to 3y minus 6. Now that I have the value here of x, I can substitute this value of x into my line 2 right here. Again, it has to be into the other equation, not into the first equation that I used. Okay, so the equation that I solve for, I can't use to plug back in. So when I plug this back in to my line 2, I'm going to say 3x, which in this case is y minus 6, because we're substituting, minus 9 is going to be equal to 9y. Now I'm going to go through the process of simplifying this. So I get that 9y minus 18 minus 9 is equal to a 9y. So I'm going to combine these here and get 9y minus 27 is equal to 9y. But then when I go and like subtract 9y, whether I think I'm subtracting from this side or from this side, if I have to do it to both sides, I get negative 27 is equal to 0. And this is crazy here because what just happened? When you get to this point, you might think, oh my hell, what did I just do wrong? But you didn't do anything wrong. This right here says that negative 27 is equal to 0, and negative 27 will never equal 0. This is a false statement. Okay, well, what the heck? Where'd the variables go? Well, when the variables disappear and you have a false statement, okay, then these lines will never intersect. And the reason why is because if we were to put these in slope-intercept form, you could see that they're parallel. Okay, so algebraically, what happens here? Well, algebraically, when I'm solving for parallel lines, I end up getting a false statement. So I get something like 2 is equal to negative 5. So this is completely false. I get some false statement with no variables. You can see there's the variables dropped out. There's no variables here. Okay, well, if you get a false statement here with no variables, then you have no solution. Okay, I just write that the solution is the empty set. There is no solution here. Okay, again, I said if we were to put both of these lines into slope-intercept form, you could see that they're parallel lines. They would have the same slope, but different y-intercepts. Okay, so this is algebraically, okay, what this looks like. I would get some false statement. All right, let's do 2 more examples here. Okay, my line 1 this time is going to be x is equal to 3y minus 1 and 2x minus 6y is equal to negative 2. Okay, so what do I get here? Let me make sure that this is, I moved it. Okay, so here, this one, they were real nice. They already solved one equation for one variable, so sweet. I'm just going to take this value then, if this is x, I'm just going to plug it right into here. It's made my life easy. So I'm going to get 2 times 3y minus 1 minus 6y is equal to negative 2. Okay, I'm going to simplify here, get 6y minus 2 minus 6y is equal to negative 2. These are on the same side, so I'm going to combine them. 6y minus 6y is 0, so then I get this negative 2 is equal to negative 2. And you're like, whoa, what the heck? Where'd the variables go again? Well, they're gone. Okay, so if I get a true statement, such as this one, which is a negative 2, so let's say that it just says, you know, negative 2 is equal to negative 2, and this statement is true. What this means when you have no variables, okay, is that these are the same line. If I put them in slope-intercept form, which I think I'm going to do real quick just to show you. If I put line 1, let's do line 1 in blue. If I put line 1 in slope-intercept form, if I add the 1 to both sides, I get x plus 1 equals a 3y, divide everything by 3, and y then is going to be equal to 1/3 x plus 1/3. So line 1 is y is equal to 1/3 x plus 1/3. Line 2, if I were to take it and solve, I get negative 6y is equal to negative 2x minus 2 when I divide everything by negative 6. Then I get here again y is equal to a 1/3 x plus 1/3, and you can see these are indeed the same line. So algebraically though, because we didn't graph them, algebraically what happens is I get a statement where the variables drop out, where they sum to 0. Okay, there's no variables left, but it's true. When it's true, they're infinite solutions. So what is the answer to this question? What is the answer here? It's not 1 point, it's not that there's no solutions, it's that there are infinite solutions. Okay, infinite solutions. And how do we write this infinite solution? Well, it's kind of a tricky way. What will happen is we'll say, well, if there's an infinite number of solutions, how do I know which solutions are the correct ones? Because remember, not all ordered pairs are. Like the ordered pair over here, or the ordered pair over here, or the one over here. Those are not solutions to this system because they don't lie on the line. So how can I say what the solution is? I'm going to say x and y are such, so the ordered pair x and y is such that it's any point that lies on this line, the original line that was given. So if it lies on this line, then it's going to lie on this line. So this entire line is the solution. It's the infinite solution because this line goes on forever. So the way you write infinite solutions is you write typically just the first line that they give you. Okay, again, all this means is any ordered pair that would make this statement true would also make this one true. Okay, but that doesn't change there's infinite solutions. This is just the specific infinite solution. All right, let's do one more with fractions. And we will talk about couple things real quick. So my line 1, I'm going to have x over 8 minus y over 2, and that's going to be equal to 1. And I'm going to get x over 3 minus y is equal to 2. Okay, so we've got line 1 here and line 2. All right, in my system. Well, first of all, these have fractions, and I don't want fractions. So what I'm going to do for all of my equations here is I want to clear the fractions. So how do we clear the fractions? Let's go through those steps again real quick. Clear fractions. Well, I'm just going to choose an LCD for this top equation, and I'm also going to choose an LCD for the bottom. So the LCD for the top here is going to be 8. That is the least common denominator, the smallest multiple of all the denominators. The LCD for the bottom equation, I'm going to treat them separate, they're separate equations, is going to be 3. This is over 1, this is over 1, and I'm going to treat them separately. Okay, I'm treating them separately in getting rid of the top equation. I'm going to take and multiply or make each of the denominators 8. So this is the building up version. So I'm going to multiply this by 8. So my new line 1 equation, let's write that right here. My new line 1. If all the denominators are the same, then I can just wipe the denominators out. And the new line 1 is x minus y, x minus a 4y is equal to 8. Okay, so now I'm going to do the same thing with line 2. I'm going to say I need all of these denominators to be 3. So to do that, I'm going to multiply both the top and the bottom by 3. And when the bottoms are all the same, then I can delete them or just get rid of them. The reason why we can do this is because I could just say, well, if I just multiplied the entire equation by 3, then this is what would be left. I would get an x minus a 3y is equal to 6. Okay, so since this is the case, now I've cleared my fractions. If I have my fractions, I want to clear them up front. Then I'm going to say, okay, well, now what variable or which equation do I want to solve for which variable? Well, it doesn't really matter at this point because they both are only one step to solve for x. So no problem here. We're just going to say, all right, well, let's solve equation 2 for x. I'm going to add 3y to both sides, and I'm going to get that x is equal to 3y plus 6. Well, if this is the value for x, I'm going to take that value, remember, and plug it into the other equation. So I solved line 2 for x, so I'm going to plug that into line 1. When I plug that into line 1, I say that x is 3y plus 6 minus a 4y is equal to 8. I'm going to subtract the 6 over and combine these. So I get a negative y is equal to 2 when I divide by negative 1. Then y is a negative 2. Great. Y is a negative 2, so I'm going to take that value now and substitute y equals negative 2 into an original equation. Well, that's going to be ugly, but we can do it. I'm going to plug it into line 2 here, so I'm going to say that x over 3 minus y, which in this case is a negative 2, equals 2. Well, that means that x over 3 plus 2 is equal to 2, so I'm going to subtract 2, and I get that x over 3 is equal to 0. To get rid of that 3, I'm going to times both sides of the equation by 3, and that means that x is 0, which is fine. X can be 0. Again, anything times 0 is 0, so x is 0. So this is the x coordinate of my solution, and this is the y coordinate of my solution. It's important to note here that I get one unique solution. That means that these lines do intersect, and they're not coincidental, they're not the same line, and they're not parallel lines. They cross at some point, and the point where they cross is the point 0, negative 2. So algebraically, again, this is what this looks like. So you can notice here, one more time, that x or y, and I should say x and or y, can be 0. 0 doesn't mean that they're parallel or coincidental. It just means that the value of x or y is 0. Okay, so algebraically, this is what they look like. These are the type of solution that they are. Graphically, this is what this looks like, and this is substitution. I'm going to stop this video again, and the next video is going to be 4.1 part 3, or 4.1 elimination, and we will talk about that.